Good morning, everyone. I'm Shubham Tanwar, a PhD student in the group of Professor Gabriel Gomila at IBEC. Today, I'll present a recently published work in Advanced Functional Materials on nanoscale mapping of electrical properties of an electrolyte-gated organic transistor. This work is done in collaboration with the groups at ICMAB and the University of Manchester. The organic transistors have shown a lot of progress in last 2 decades, complemented with the Nobel Prize in 2000. They have given us the devices that shows qualities like biocompatibility, flexibility, and low cost. The organic transistors are generally used to study these organic materials. Here, the charge carriers can be injected into the material with the help of the gate voltage and can be driven across the device with the help of the drain voltage, giving us its output and transfer characteristics. From these characteristics, charge carrier mobility, threshold voltage, and on and off ratios can be extracted, which are the macro scale parameters, but they don't give us the nanoscale properties. These materials are generally made using solution processing or vacuum sublimated. That shows nanostructures because of presence of polycrystallinity or different phases of the materials. And all of these leads to heterogeneity at the nanoscale. So we need a scanning probe microscopy which can probe these nanoscale structures and during operations. So scanning probe microscopy is a must. Measurements in air are pretty standard now, but when we do measurements in liquid, there is a lot of complex phenomena that we have to take into account, which is necessary for applications like biosensing. To do nanoscale measurements, in liquid, generally the transistor is gated with the help of the cantilever here as shown here. And to make the nanoscale measurements in such devices, we have to overcome one phenomena, which is charge screening dynamics. When we apply negative gate voltages for a p-type semiconductor, the ions in the solutions comes into motions and they accumulate at the tip as shown here. In the tip there are positive ions and in the tip itself there are electrons, and it forms something called a double layer. It's basically a capacitor. Since double layer is like a capacitor, it blocks the DC voltage, but it lets the AC pass through, but not that effectively. It depends on its frequencies. If we want to probe semiconductor electrolyte interface, the voltage has to arrive there, and it's not possible with a DC voltage because ions block that. So we have to use an AC voltage, but at what frequency? The frequency depends on the charges. And let's, for an analogy, take that these charges went to the disco and they are following the beat. And if the beat is at low frequency, they can follow it easily. But if it's very high, they really starts to phase out. At very high frequency, they can't even hear it. So it's really difficult for them to follow. And let's say if we have another beat, which is following at a very low frequency, and both of them we are playing at the same time. Now the charges can follow the low beat, but cannot follow the high beat. So in such a case, we can make use of low frequencies to modulate, let's say, our materials properties, and then we can use high frequencies to probe it, and that's exactly what we do. We apply beats in megahertz frequencies with a DC voltage which modulates the conductivity. In our AFM setups, what we do, we take electrical force curves at each pixel of the device when the device is operating. That is, when we are measuring its global characteristics as well. It gives us characteristics at the global scale, like generally that we get in air measurements, and then we take images at different gate voltages, like when it is going from off to the on state. And here you can easily see that there is a change of color, the change of contrast in the images when it is going from off state to on state. And in these images, there is a heterogeneity that you can easily see due to the contrast within an image. If we wanted to further examine these heterogeneities, we have taken a closer look at what happens in the very channel. Here you can see in the topography we cannot see much, but in adhesion and phase we can see structures, we can see heterogeneity, and it tells us that there are heterogeneous materials and there are different phases and materials within the semiconductor. And in the electrical images you can easily see that they show a contrast. And in such materials, even a 1 nanometer patches can be easily distinguished with this technique. So these techniques is very effective in telling us about the heterogeneity at the nanoscale in liquid measurements. This might sound simple, but this is the first time that such mapping could be done in liquid. And this is just the start. By using these mapping techniques, we can make these beautiful images which are a function of conductivities and interfacial capacitances. And with the help of these, we can optimize our devices. And if you want to know more details, you can check out my posters, and I'll see you there. Thank you.